What if there was an idea, a new theory of gravity that could bridge the gap between our predictions and observations of the most mysterious substance in the universe, dark energy?
Everything connects with gravity. Everything lives in your space-time.
Dark energy is a force that scientists believe is causing the expansion of the universe to not only increase, but to do so at an accelerating rate. But there are discrepancies between the predicted amounts of dark energy in the universe and our theoretical calculations based on the properties of the fundamental particles that we know and love. We're trying to get to the bottom of this for years, almost 30 years without success. That is, until today's guest, Professor Claudia de Rham, proposed a new theory of massive gravity that could explain why the universe is accelerating and also solve the impossible dark energy puzzle.
It's really in asking ourselves provocative questions just like you do that we make progress.
Join Claudia and me as we fall headfirst into the dark side of the universe to uncover its most seemingly impossible mysteries and turn the impossible into the inevitable. Let's go. Claudia, how are you doing today?
I'm great. Thank you. How are you, Brian?
I'm excellent now that I get a chance to talk to you. We have a lot in common, but I'm going to start first with a rather provocative question, if you'll indulge me. A lot of this book and a lot of your work corresponds to the desire to find a solution to the so-called mass of the graviton. I want to start by asking you, why should we care about finding the mass or attributing mass to a particle whose existence we don't even know for sure about?
So that's many different reasons. The first one, I would say, which is going to convince the few people, but it's the truth, is because we as humans care about understanding nature at the most fundamental level. And so we should really always dive deeper and deeper. That's how we make progress. And sometimes it's really in asking ourselves provocative questions, just like you do, that we make progress, and questions that may not have a specific outcome for tomorrow, but it ultimately has shaped us, shaped the future of humanity. That is really the real reason. But then there's many other reasons I can tell you of why I went into that specific question. First, let me just say that it's about understanding whether a fundamental particle, which we may never detect per se, has a mass, but it has an implication also on gravitational waves, which we have observed. And actually, from the very first direct detection of gravitational waves here on Earth in 2015, the first thing that they were able to do is put an upper limit on how massive the graviton was, because it had an effect on the propagation of gravitational waves. So now that limit is still quite high as compared to what we ideally would like it to be, for the reasons I'll explain. But still, in principle, it has some real consequences that we can observe here on Earth through gravitational waves and through many different tests of gravity, tests of the universe, tests of why we're here, where we're going, our origin, and all of those questions. Why I am interested, why I do spend my time looking at that as opposed to all sorts of other fundamental questions, is because I think it has a potential to tackle the most challenging question of fundamental physics, the biggest discrepancy of the whole history of science, which is the cosmological constant problem. Or in other words, why are we living in a universe that looks the way it does and is not actually expanding at an accelerated rate, which is way faster by at least 56 orders of magnitude, if not 120 orders of magnitude, as should be the case if the quantum fluctuations from all the fields that we know exist, like the electrons and the Higgs and all of those fields, all of those other fundamental particles that made us so really exist, we would expect them to lead to what we call an energy in the vacuum, an energy of nothingness that fills the whole universe itself and should lead to a hugely faster accelerated rate of expansion of the universe. And the discrepancy is simply the biggest discrepancy in the whole history of science. And that is at the interface of the two pillars of modern theoretical physics and modern science, which on one side is gravity, on the other side is field theory, quantum field theory, putting the two together, which is really the foundation of the standard model of particle physics as we know it today. And so it's very much at the interface between the two of them that we have the biggest discrepancy we can ever imagine. And so it seems natural that the resolution is very much at the interface between the two of them, thinking of gravity as well as a quantum field theory and understanding what are the properties of gravity more fundamentally.
So recently, the DESI collaboration made an announcement that there seems to be evidence for the variation of the cosmological constant from constant to perhaps a contestant-like behavior. Can you tell me how would that impact the statement you just made? Would it affect the search or the motivation to look for a massive graviton?
So it is within the same framework that something has to be slightly different as compared to the standard, I'll call lambda CDM or vanilla model for the cosmological paradigm, which we would just think until now, everything seemed to fit beautifully with having cold dark matter and a simple cosmological constant. So very natural in that evolution sense. In a parameter sense, it's very simple in that sense, but actually in understanding how that fits in the bigger picture is that's where the real naturalist questions come in. And so if there's any departure from this lambda CDM, it really opens up the opportunity for there to be something else out there. And any modification of gravity could feed into that. Any dynamical dark energy could feed into that. And sometimes there's a little bit of a muchness on how much you consider modify gravity and dark energy. Some models of modification of gravity can be recaptured in effectively looking for cosmological purposes as a dynamical cosmological constant, or dynamical, shouldn't say cosmological constant, but dynamical dark energy. So for instance, if you're in a theory of massive gravity and you want to tackle the cosmological constant problem with that, you would want to accept that the universe is filled with vacuum energy as expected from particle physics. But this huge level of vacuum energy doesn't lead to a huge accelerated rate of the universe today. It did in the past, but then through the weakening of gravity due to the mass of the graviton, through the evolution of the universe, you would have a relaxation of the effect of this vacuum energy on the evolution of the universe. So in some sense, it does look like a dynamical cosmological constant, and that seems paradoxal, but the source would be constant in some sense. It would be vacuum energy, it would be a cosmological constant, but then its effect on gravity, its effect on the evolution of the universe would be dynamical. It would be diluted, relaxed away through the evolution of the universe. And so we would expect, indeed, this type of departure from the standard lambda CDM, the standard cosmological constant.
So some of your work in this book, which we will now play my favorite game about, called Judging Books by Their Cover, is about a topic near and dear to my heart, the cosmic microwave background, and the subject of polarization. But before we get there, I want us to indulge ourselves in this game that I call Judging Books by Their Covers. So Claudia, please, if you would, take us through the beautiful artwork, the title, and the subtitle of this wonderful book.
Okay, so the title is The Beauty of Falling, and the subtitle, A Life in Pursuit of Gravity. And I'm really happy to go through what I mean by all of those things, which is a lot. But I'm very happy with the cover, actually, because it's very symbolic of the story. There is a real story in the book. So on the cover, you start seeing on the top an astronaut floating in midair, experiencing some level of free falling and some freedom, very much some freedom in that. And then in the middle, you see the same person, I think, a lady, falling now. You can imagine she's falling on Earth. She's really embracing some level of free fall. There's probably some friction from the air because she's falling on Earth, but she's enjoying it. There's a beauty in the fall itself. The fall itself is beautiful. Maybe what comes next is what was a bit more worrying. But luckily for her, the last picture at the bottom is her diving in the sea and really enjoying this last part of the free fall and seeing how this channel, how this falling has been channeling through a different perspective now enjoying playing with gravity as she dives in the ocean and enjoying this new environment.
The subtitle is beautiful, and of course, a lot of these things on the cover that this character is experiencing are relevant to you. The first one being astronaut, which you have attempted to be from the European Space Agency side. The middle one is you, flying, maybe doing a dive, but there's an airplane in the back. You and I are both pilots. I don't know how much you fly nowadays, but I have flown a Diamond Katana before.
Amazing.
Yes, exactly.
Yeah, I love that happening. I have a picture of it there. I'm not going to tell the screen right now, but I love that happening. It just wants to fly. It's amazing. It just pull the nose up and it wants to fly. It's incredible.
And then there's the woman ends up underwater wearing a scuba diving suit. And that takes me to my first question from my guest, an audience member who's a very special person to both of us. His name is Professor Greg Gabadadze, who is not only a friend and a brilliant scientist and innovator, truly just one of my heroes in science. He's also an administrator at NYU, a dean. I don't know what masochistic desire he had to do that. He's from Georgia, not the state, but the country of Georgia. So, they make tough people there, brilliant and tough. But Greg asked me to ask you when I solicited a question. He said, "Thanks for reaching out. Claudia wrote a wonderful book with a clear and modern perspective on physics and also connected to remarkable personal experiences." And I would have a fun question for Claudia. I'd ask her if there might be any advantage to thinking about physics while floating in the cosmos or underwater. And I want to get your answer to that, Gregory's question.
In both ways, I think. Being a theoretical physicist and thinking about quite abstract concepts, I think there is a beauty in doing that when you fly or when you dive, you float in the cosmos, in embracing this understanding of nature at a deeper level. There is a deep connection that gets there. But also the other way around. Of course, I would like to tell you that I'm an astronaut and I'm doing experiences about gravity in the microgravity on free fall and orbit around the Earth. That hasn't happened, and I'm not doing that when I'm when I'm scuba diving. I'm not doing some explicit state-of-the-art test of gravity when I do that, but I do it with my body, and I think there is, as you say, Greg is a very tough guy, and I'm not saying that we should all be very tough, but there is some level in which learning to have this balance between judging your instinct, judging your intuition in very challenging situations, but also seeing how much you can judge intuition and how much you have to rely on your confidence to follow a pattern, to follow the logic, to follow scientific rules in situations where actually your instinct naively would tell you to do something which would be quite catastrophic. And you're a pilot, you know that, for instance, if you're flying and you're stalling, naturally, if you hadn't had any training, the first thing you would try to do is pull the nose up, because you say you're going down, you're going to pull the nose up so that you pick up altitude. But actually that decreases the lift, and so the plane sinks much more, and that can actually lead to an accident. So following too much instinct in these situations can lead to catastrophic outcomes. And so if you learn to put yourself in uncomfortable situations and have this balance between knowing what to do, there's a level of instinct that you learn after having practiced it for hundreds of times, but also it's very much based on scientific understanding. You understand what you have to do logically, that makes complete sense, and then you train yourself to learn the process in that. With your body, a situation where your life depends on it, then you can do that on the blackboard. It's so much easier.
Hey there. While dark energy is one of the most mysterious concepts in the known universe, another mystery I'm trying to solve is why only 50% of you out there are subscribed to my YouTube channel or following the podcast on your favorite podcast app. Are you one of them? Please, don't be in the silent majority. Do me a favor, subscribe, follow, and leave a comment or review. It really helps me out, and I respond to every single one. And when you do it, it helps me get great guests like Claudia, Dan Dennett, Sam Harris. It's all a numbers game, unfortunately, and we have to make sure the algorithm respects the matter that matters that we discussed on the Into the Impossible podcast. So before we get back to the episode, just take a second and hit that subscribe button, leave a comment or a thumbs up. Anything will help out. Appreciate it. Now back to the episode. And that brings me to my next question, which is related to this gentleman who features very prominently in this book, Albert Einstein.
Yes,
and as you know,
yeah.
Oh, you do? Okay, we can have a dueling one. So I'm going to do something mean, which looks cruel, but actually was one of his most exciting breakthroughs. In fact, he called this the happiest thought of his life, which was that if he was falling, he would experience no gravitational force. And that led to the Einstein equivalence principle. And I want to ask this as a first detour into your life as a professor and say that nowadays we hear a lot about artificial intelligence and machine learning and all sorts of things. I think they're very powerful. But as a professor, I think about, well, how could these things aid us? How could they be better researchers? Could such an entity, artificial, made of silicon and glass and steel and whatever else, could it experience the joy of falling? Could it experience this most exhilarating feeling of Albert Einstein? And then if it could experience that viscerally with a body, or if it could not rather experience because it doesn't have a body, how could it make a breakthrough equivalent to what Einstein, the greatest scientist of the last 100 years perhaps, how could it even be considered to be intelligent if it can't even do what Einstein did? I mean, it's a high bar, but do you think that physicists can be replaced or mimicked even by artificial intelligence?
I think there's no replacement. I think we've done so well at using things to our advantage, and there's clear advantages to using machine learning. It can speed up a lot of the things. Now, when it comes to can it feel for us? That's a deep question. I can't do I really feel something, or am I in a matrix and believe that I feel something? And how will I know the difference? I don't know. I think related to your question is also how we model the world all around us. If a computer is able to model the world, the universe, and nature all around itself to incredible precision, does it make it that this model is the reality or not? And there's a thin line there sometimes. So your question makes me reminded of that. If a computer can reproduce all the signs of what it means to feel something, does it make it feel it or not? You'd think not, because we are experiencing something deeper than that. But how can you tell? I don't know. It's very philosophical. It's way beyond.
Yeah, maybe I'd say at least.
But I do think that there is a difference between speeding things up and reproducing, relying on past understood patterns or past patterns that haven't necessarily been understood but have been identified, and seeing them and being able to get some sense and logic and organizing all of that, particularly when it comes to huge level of data, to speed up some connection between some patterns and some model and some values that you want to take out of these patterns or these data. There's a huge difference between doing that and actually coming up with a breakthrough in itself, which requires a huge level of creativity. It's like all of a sudden thinking you're going to paint the world, but not with pencils and paint, but using another dimension. And it's something I can't even capture in words. And so if you haven't taught the machine to think in that language, to use tools that will rely on the extra dimension, let me just be crazy out there, how could it? I don't think you will out of the blue come up with things we haven't ourselves yet invented with a completely new language. And so that level of creativity, I think we will always have. And it's a little bit different. I should say that the response to that, some people say that computers through machine learning, they can come up with new songs. And so that shows some level of creativity. But those new songs are still within the same remit of previous songs, still with musical notes, still within the same sense of that. It will be quite different to all of a sudden think of a new channel of communication, which is not through sound, is not through light is not even through gravitational waves, that would be something yet completely different. And that's what we scientists are very good at, to think about new ways to connect with the world.
And in a 2020 paper published in PRD, you described the speed of gravity. I always tell my students, to their great horror, the sun could disappear right now, and God forbid that happens, but we wouldn't know for 8 minutes. But is that really true? I mean, how do we know if that's actually true? So your paper, The Speed of Gravity, with Andrew Tolley at Imperial as well, makes a prediction that the speed of gravity could differ from lowercase c, and I'm surprised. Why hasn't this made a bigger impact? Why weren't you?
It's beautiful.
Why aren't you even more famous than you are?
Yeah, you need to do that. You can imagine gravitational rainbows where the speed of gravity does depend on the frequency, just like light depends on the frequency. So not in the vacuum, not in empty space per se. For light, we can understand, I can sort of conceive what empty space is. It's the absence of interactions between light and anything else. So we are used to the fact that light in space travels at the speed of light. But if you shine light through water, for instance, then the light will start interacting slightly differently with the medium, with the water, with the water molecules, depending on the frequency of light. And so you see that, and because of this interaction, light doesn't travel at the speed of light in the vacuum in water. And the way it travels, the speed at which it travels, depends on its color. So we're all used to that phenomenon. We all see rainbows, and that's the proof that light doesn't always travel at the speed of light. Now, so you can ask yourself the same question for gravity, and that's it's quite subtle, because now what does it mean in empty space when actually everything connects with gravity, everything lives in your space time, and if our universe is filled with dark energy, then is there such a thing as empty space? I don't know. And it could be that gravitational waves do interact ever so slightly with anything living in that space-time, including dark energy. And if that were the case, then it would modify the speed of gravitational waves. It would do so at very, very low frequencies. So if all of a sudden you were to take off the sun, that would be kind of a high frequency, a high frequency thing. And so the propagation of this information, you would expect it to take very close to 8 minutes to reach to us, because at those frequencies, you would expect the speed of gravitational waves to be very, very close to that of light.
And another thing that would come concomitantly with such a phenomenon would be additional polarization modes, in addition to the so-called plus and cross modes that my colleagues and I are trying to study in the cosmic microwave background. Can you explain these types of new polarization states? There's a beautiful illustration in the book about them, the so-called breathing one. That's very evocative.
Yeah.
Can you explain what these polarizations would do, and why you have to have new polarization states of gravity if gravitational waves, or you called it glite, that will maybe catch on and supplement your salary there. I hope so. I hope you get the trademark on that. But how would they manifest themselves? How would a breathing mode manifest itself? And what would it look like in the power spectrum of the CMB that my colleagues and I in the Simons Foundation have supported to the tune of over $110 million so far? First
of all, I think we all sort of accepted that for instance, light itself comes in two polarizations, and you put some very cool sunglasses, and then you see maybe one polarization and the other one gets filtered out. And you can ask the question already for gravitational waves. Can you put some cool sunglasses for gravitational waves and only see one polarization or the other one? Well, that would be a bit more challenging. But already, yes, gravitational waves, or what I like to call glide, because on some level it's quite similar to light, comes already in two different flavors. And that's imposed by symmetry according to Einstein's theory of general relativity. Now imagine that gravitational waves weren't traveling at the speed of light, very close to the speed of light, but not necessarily weren't forced anymore to travel at the speed of light. Then you could in principle imagine some sort of analog to sound waves, some longitudinal waves, where you could have some gravitational waves speeding up a little bit and slowing down a little bit. So these would be modes which would not look like the standard gravitational waves, the cross and the plus, which are transfers to the line of propagation of the gravitational waves. They would actually be along the line of propagation of the gravitational waves. So that mode, we typically don't like it, but that's a different story, is just to illustrate the fact that you open up a whole set of other possibilities once you allow yourself to think beyond the box, beyond, not that I want to put Einstein in a box, but beyond the theory of Einstein, theory of general relativity. And so in addition to these longitudinal modes, you also have some modes which are in between. So they're half through the transverse direction and half through the longitudinal direction. And also related to that, you can now start imagining quite different things where rather than just have the plus and the cross mode transfers to the propagation, you could have a breathing mode. Really just think about breathing. And if you think of some beads distributed along a circle, as that mode goes through, they would sort of seem to shoot as a bigger circle and then come to a smaller circle and bigger circle and smaller circle. There's something quite Pacific about that. I like this picture. It makes me feel meditating as that mode goes through. That mode is actually very important in any theory of gravity beyond Einstein's theory of gravity, because that is typically expected to be the smoking gun signature for a theory beyond Einstein's theory of general relativity. That mode, the real question is, why isn't it there in Einstein's theory of general relativity? You could expect it to be there in principle, and it's not because of symmetry. Einstein's theory of general relativity was based on the equivalence principle and on some other principles that nowadays we understand them as being symmetry-driven, and that symmetry simply prevents this conformal or breathing mode from appearing. Now, you can think if the graviton had a mass, you can always make that mass sufficiently small so that you don't see any departure. And that is true. That is true in principle. However, because now there are additional polarization for gravitational waves, you can think about having different ways to communicate through gravity. There's different channels of communication through gravity. And that has a big impact in how we test in gravity. As you say, that could mean, for instance, that at the very beginning of the universe, you could have production of not only primordial gravitational waves as the one you're thinking about, which would lead to polarizations in the CMB, but you could also think of production of primordial gravitational waves in this breathing mode. Now, this breathing mode in itself, from a cosmological perspective, it wouldn't be, during inflation, it wouldn't necessarily look so dissimilar to the inflaton itself or to other fields that are already present and whose effect has already been seen imprinted in the CMB through the temperature fluctuations. So actually, there are models out there of massive gravity for the very beginning of the universe, where this additional polarization of gravitational waves do act potentially as a substitute for the inflaton. And for the fluctuations in those primordial breathing mode polarizations would lead to the temperature fluctuations that we do see in the cosmic microwave background, for instance.
So would there be a modification to the BB mode power spectrum, the autocorrelation, or would it induce new forbidden correlations, AB correlations? Would it change the shape of the autocorrelation? Is there some way to detect it? Because these are this is all you have, right? You make the case in the book that beyond the realm of the galaxy or even clusters, there's no hope of discovering physics of gravity at the Planck scale other than inflation. If inflation did take place, we don't know that it did. Some of us hope that it did, but we've had that dream before. But the question is, are there new observable signatures that we can use to detect the presence or absence of a massive graviton and the concomitant breathing modes that would also be induced in novel polarization states?
Yeah, so that's a great question. One of the things that would happen is if if the mass of the graviton is a little bit too large, if you imagine you have graviton being too massive, then it would prevent the production of primordial gravitational waves whose frequency are comparable as the mass of the graviton during the period where they should have been produced. So, in effect, what you would expect in the power spectrum of primordial polarization of primordial gravitational waves, let me say, of B-mode polarization, you would expect a plateau. You wouldn't expect any production of primordial gravitational waves at very low L, because those would be forbidden by the fact that the graviton prevents the production of primordial gravitational waves within those scales. So seeing actually the production of primordial gravitational waves, a CMB polarization B-mode spectrum at very low L, that would be a sign against massive gravity, against a massive graviton, or against massive polarizations during the period of inflation.
One thing that people don't talk about as much, I mean, people don't talk about this massive gravitons very much either, but comparatively, even if you can imagine, even less attention is paid to the existence of spin 3/2 particles. We have a spin 0 particles. We have abundance of those. We have a lot of spin 1/2, thank God, or you and I wouldn't be here talking. We have plenty of light, with an L and no G in front of it. We even have hopes of Glite with spin, but they're absent, the so-called black sheep, maybe the missing, missing term, missing spin statistic term is spin 3/2. Why? What did nature do to so alienate one of the most prominent types of fundamental intrinsic spin modes that could possibly exist?
Yeah, it's a good question. I don't know. I don't know. I mean, those particles, not at the fundamental level, but at composite level, they do exist. So we know they can be represented to some level in nature. But having them as fundamental particle, we know that then their interactions with other fields is very difficult, and their implementation within a theory of gravity is also very, very challenging. I know that for spin 2, and it's just the same case for spin 3/2 as well. The framework in which you construct the nonlinearities, the interactions for spin up to 1, is relatively straightforward, I would say. And the connection with gravity as well is relatively straightforward. But when you go beyond that, it becomes extremely complicated, and you have to be very subtle in how you try to connect those modes with others, how they communicate with others. You very easily open new channels of instabilities. So it's not typically you can just add some level of interactions and you're okay with that. As soon as you open up a smallest level of interaction, you need to reinvent the wheel, if it so says, reinvent a whole framework to see how they embed into a deeper one. So that we see from the theoretical perspective how challenging it is. And so maybe because of everything that comes along with it, it's much harder for them to manifest themselves in nature.
Hey there. Dark matter is mysterious, but ordinary matter can be had in the form of a meteorite. If you just do me the favor of joining my free Monday Magic mailing list, where I send out the coolest, most interesting information in all the known universe. I don't sell anything, nothing else to do, just share my passion with the cosmos, and all my guests also subscribe to this newsletter. So you're great company. You go to briankeating.com/list and you'll be entered to win an actual piece of space dust, a meteorite from the early solar system. And if you have a .edu email address, you automatically win. Go to briankeating.com/list or briankeating.com/edu if you have an edu email address. Now, let's get back to the dark side of the universe with Claudia de Rham. Very interesting. I think another question that my listeners and viewers might have is this concept of extra dimensions, which plays a big role in your research. Is there any difference between when you speak about extra dimensions and when string theorists or fundamental particle physicists speak about it? They both require or mandate the existence of these things which are as yet undetected, as you say in the book. So what is it? Are these extra dimensions related to the extra dimensions of string theory? And if not, what are they?
The way I think about them doesn't preclude them from coming from string theory. But actually, the concept of extra dimension is a very, very old one. And within the framework of general relativity, the same modern framework as in which we understand them today, they were already proposed by Kaluza and Klein. So very, very shortly after the proposal of general relativity, they are very natural extension of general relativity. They have a sort of taken a comeback since string theory because string theory needs them. If you don't think of string theory, you can ask yourself as to why we live in a world where there is 3-dimensional space and one of time. You can ask yourself, why is that the case? But you don't necessarily believe that there needs to be additional one, extra one. Whereas in string theory, there needs to be extra one. There's no choice on the matter. And then they are typically expected to be confined around themselves, compactified, very small, very, very small extra dimensions, or there could be some larger ones. And there we would be confined on a membrane and a brain, deep brain in those extra dimensions. But a lot of my research in the way I've been thinking about it and looking at implications for gravity and for cosmology, that was very much, some of those ideas were motivated by string theory. I don't necessarily need to have string theory to think about them, but a lot of them nowadays, they are motivated again for one another. In themselves, they're actually very natural. One of the questions, I think to me, one of the most fundamental questions there is why 3-dimension? And you mentioned Robert Bronnenberger earlier. He's an incredible physicist, but he's one of the physicists that has come up with the most ideas on why it is that we are experiencing 3 dimensions. Even in string theory, we understand there are extra dimensions, but precisely what is the mechanism that led to us living in a universe that experiences 3 dimensions is something quite challenging, and it's not natural at all in string theory. It's very hard to make that work. There's no natural process. He and collaborators of him, also Ann Davis and with Durer have been exploring the idea of how dynamically you can have a sort of a selection mechanism that either picks out membranes in extra dimensions which are 3+1 dimensional. It's almost an evolution selection mechanism where those are the ones we end up living in. Or some other types of mechanisms in why the other dimension would be confined, compactified to be very small, and we only experience the ones we do. But even in both case scenarios, assumes the existence of other dimensions out there, and that could have consequences on us. To see the consequences of that, typically you have to go to very high energy scale to be able to probe those extra dimensions, and that corresponds to going again back to the very early universe, again to the type of research that you're doing. And it is possible, and I would hope very much so, that there could be imprints on the very early universe of those extra dimensions, and that could be imprints on the power spectrum of the CMB and B-mode polarization, possibly. That's for you to tell me, actually. They can be, in some other models of extra dimensions, they can be some effect actually not at very high energy, but at very low energy, that things will look very similar to, look 4-dimensional, 3+1. And I say 4-dimensional, I mean 3 of space and 1 of time dimension for our everyday life. But as you go to larger and larger distances, on cosmological distances, then you're able to start probing the extra dimension. And that's why the evolution of the universe nowadays seems kind of counterintuitive. And that's because we're starting possibly to probe the extra dimensional space.
So it's a sort of a relic or a shadow of the higher dimensions that we perceive.
Yeah. There's a lot of models out there where our cosmological evolution, what we live as a universe, is really, as you say, a reminiscent or a shadow, a consequence of our motion through time, yes, but really through the extra dimensional space. We are traveling through this extra dimensional space, and that has an effect on our universe as a whole. with just a consequence of that.
Question I have for you, perhaps to elucidate, and I've asked it of many scientists, but I never really get an answer that I can try. And I've asked even Roger Penrose and his multiple occasions of being on the podcast.
and then you hope I have an answer.
Well, I hear what he says, but I don't know if I understand what he says. Although that might be due to my failure to have consciousness, according to him. But my question for you is. First, do we need a quantum theory of gravity? I mean, the only two scenarios where quantum gravity seems to pertain in any kind of important, impactful, relevant role is not in our daily lives, but are at the singularities of black holes and perhaps the origin of time, if indeed time had an origin, and many people don't believe that it did or was a classical bounce, or different cosmological models. Past guests Paul Steinhardt, Anna Aegis, Neil Turok, many others don't believe in the singular quantum gravity necessity. So why do we need a theory of quantum gravity if these only two realms that we know about are shielded by event horizons? What's the point? We'll never be able to witness this anyway.
So actually, I am working on some understanding how to make that connection. So you probably want concretely to understand how to compute those things in situation that we will likely never experience ourselves. That is true. But at the same time, we want to understand why we live in the world we are living in. I think we all ask ourselves those questions. It's all part of the origin, why we're here, why is life here, why universe is here, but even more fundamentally, why is a representation of nature, a representation of space-time here? And that the answer is, I think, seated in a theory, a more fundamental theory of something that unifies, again, not only the fundamental forces of nature as we know them with the weak and strong forces and electromagnetism, but also gravity. And this unification could have some consequences of what is our deep down, our origin in terms of what is the origin of space-time itself. I think we talked about that at the beginning already. Why are we pursuing some such fundamental questions that we'll never be able to really experience the consequences of them? And history has told us that often we think that would be the case. Einstein thought that gravitational waves will never have any consequences to our life. No connections to reality. And we do use them now to communicate in some sense. Maybe communicate is a big word because that insinuates a two-way communication, which is not the case so far. But we do communicate with them, with the universe. We use them as a new window, as a new way to see our universe through gravitational waves. That's an example where 100 years ago, we thought there's never any use to it. And yet we're here. They are real. We have detected them. So the fact that I can't tell you right now whether we'll ever be able to experience a situation where quantum gravity is needed to predict what happens precisely doesn't mean that there wouldn't be one. But who is to answer that? If we don't know what it is, we'll never be able to even answer that. I think we need to explore beyond what we know to be able to see how much more there is out there and make sense of all of those things. Let me go back, though, to a point, because we do say, for instance, I'm not a string theorist, so I can say that. I'm not a string theorist.
Nobody's perfect, Claudia. Nobody's perfect.
I'm not a string theorist, and I'm quite agnostic on whatever is going on at very high energy. And some of my colleagues would not talk to me anymore for saying that.
Which, by the way, I have to interrupt you, and pardon my interruption, but part of the mission of this podcast is to educate young scientists and how to be a good scientist. And I just want to highlight what Claudia just said, that it's her job and my job as an experimentalist, her job as a theorist, to be agnostic. I was asked by the New York Times recently, what do I hope for? What do I really want to find with the Simons Observatory? And I said, our job is not to prove things. My job is to prove people like you wrong, and your job is to keep refining what you know about the universe, so that eventually I can't prove you wrong, but that won't prove you right. And so what Claudia just did is incredibly important, right?
That's right. It's never about proving someone right or wrong in some sense. It's more about deepening our understanding of nature. That's where we're going. And Annie, this is why the book is called The Beauty of Falling, because I will fall every day. I will come up with things which are wrong every day. I will fall. And that is important. This is the way we make progress.
Right. At the end, you say, in fact, past these pictures, that is part of the beauty, is that not that just that you fall and that, that can be, also, but part of the journey is how you get back up. Right. And how you respond to these challenges. And I think, again, just for my young students and postdocs and young faculty and old faculty who might need to learn this lesson, but the concept of quantum gravity is a beautiful one, because we have this innate need to quantize everything we see. It's done so well. But the question I have even goes, you talk about pie in the sky, and it reminded me of this past guest, Elon Musk, who I did talk to on the podcast, tangentially. You can find it on the videos and audio. But he once said, the Planck length sets this fundamental limit beyond which we don't even need to know the digits of pi. In other words, there's some minimum radius, circle, which would be the Planck length. And I responded to him. He didn't write back, but that's sort of nonsensical, right? Nothing really happens at the Planck length, right? Am I wrong about that? It is a correspondence, a numerological coincidence, but nothing more. Or am I wrong?
So what we know is that there comes a point. It's not about a distance. It never was about a distance in itself. It's about when the curvature, some measurable effect of the curvature becomes big enough. And that is not so much about what distance you can measure, but for instance, going within regions of space-time where you end up having, for instance, close to a black hole or at the Big Bang, as you were mentioning, that would seem to suggest that the curvature there becomes very large. So that a physical region where these things can happen. But understanding how we transition from the semi-classical model of gravity through general relativity, which is embedded in our quantum and in an effective quantum field theory, how we transition between that and something which is takes over when this effective quantum field theory breaks down. I think it is important to make communication between the two. And a lot of the work I do at the moment, which is not on massive gravity, is to understand what are the key ingredients that we have to keep beyond our understanding of reality, beyond general relativity. You don't even think of those concepts anymore. You don't think of space and time anymore. You think of probabilities, and you think of the notion of causality is extremely important, and it's embedded not so much into Return to the Future kind of cartoon line, but it's encoded in deep statements in how we can think of probabilities, and how we can think of also the notion of probabilities in a quantum sense, whether they respect some notion of unitarity, where if you sum up the probabilities of a given outcome, whether they will sum up to one, or whether they will sum up to something imaginary or negative, which would make no sense. And so these are very, very basic criteria that are satisfied by string theory, for instance. And you like to ask yourself, without necessarily even relying on string theory, are those concepts even correct? And is it okay for me to rely on them when all my other notions of reality have fallen apart? Is it okay for me to rely on those specific, just hang on to them to see how these very basic principles cascade their way down to something concrete at low energy, and something which is consistent with what we observe. And we can actually make connections. We can actually I can give you a model today that seems completely meaningful. I can come up with a model that can describe most of, or if not everything that I've observed today. And then I know that if I were to go back up and make a connection with how it will be realized at much more fundamentally, it will have to break some of those assumptions. It will have to break some of this assumption of unitarity or causality, or some of the way I think about these much more basic amplitudes. And so I think it is important in some sense to see what is it we're relying on at the end of the day? What are we aiming for? And we know that the way we're gonna end up describing things, nature, once we no longer can rely on even the notion of space and time to describe them, is going to be very challenging. We're going to need to invent new tools, new way to thinking to represent them. And I don't even know precisely what is the right questions for me to ask to even be able to express that. But I want to hang on very basic principles. And I think it is a meaningful question for me to ask myself, are those okay to rely on? Because if they're not, then I have to give up even more than that.
Yeah, and I guess the question I keep coming back to is what would count? What would constitute a detection of a quantum nature of gravity? And how could we do it? In the case, we have to be open to the prospect that the Simons Observatory and every other observatory may fail to detect gravitational waves in primordial nature. But that doesn't mean we couldn't rule out quantum gravity. And you and I go back in another way, in addition to Robert Brandenberger, in addition to being pilots, in addition to, well, I'm not interested in scuba diving, but we were both at Case Western, where the very first Michelson interferometer was done. And I understand from your book that, Michelson got into a little bit of a palaver, as you Brits might say. You're not British, but the point being, they used a Michelson interferometer, and now we have these LIGO machines. And my friend Eric Weinstein, came up with a beautiful thought experiment that I want to run by you as we wrap up. Imagine the double slit experiment. The double slit experiment is the most quantum of all quantum mechanical experiments in terms of manifesting truly irreproducible quantum behavior. Eric asked the question to me, and I couldn't answer it, so I'll ask it to you. Hopefully you can answer it. But if you had a double slit experiment, the electron goes through, goes through both slits, the wave function goes through both slits in some sense. But in a classical sense, could you not use the gravitational effects of the electron, just as a thought experiment? And could you not probe use the gravitational waves produced by this electron as it flies through, presumably one of the two slits, at least in Einstein's conception? So could you use these interferometers, these Michelson interferometers of LIGO, just as a thought experiment, to reveal which segment of which slit the electron went through, and therefore, kind of simultaneously be able to localize its position and momentum in a sense?
But from the gravitational waves produced by the electron itself?
Yeah, you use the gravitational waves to then measure the which slit the electron went through.
Yeah. So you need to look at what is the magnitude of a gravitational wave the electron would produce.
I'm not saying you could do it. Yeah, that was my thought too.
And that is very weak. That is going to be very, very weak in amplitude. And the issue with that is that if you have a very weak gravitational wave that goes through, then in the case of the interferometers here on Earth, then they will move the position of the mirrors, which will be below Heisenberg uncertainty principle. Now, I am a theorist, so I have no problem saying and applying for funding to say, let's build an interferometer which is of the size of the universe. Let's do that. But even if
you can get the funding, from the king.
You write the proposal, then. So let's do that.
I'll talk to Greg. You help me sweet talk Greg, okay?
Yeah, okay. I'm gonna be blacklisted now.
That's right,
and that's not credibility. Yeah, the issue is if you think about the gravitational wave produced by electron in that process, it's way too weak to being able to detect its effect. So, but there are some experiments out there where I think one of the experiments you should try to think about is having electrons absorbing a gravitational wave. And a quanta of gravitational waves. So absorbing a graviton. That's really what you want to do to test the quantum nature of gravity in a way which would be very similar to that of light. We know that electrons can absorb or emit unique quanta, discrete quanta of light or photons. And as they do that, as they change energy level around the atoms. So you want to do the same thing with gravitons. And in principle, that would happen. The probability would be very, very small, but in principle, you can imagine that would happen. The issue is always the reality of the world in which we live in. It's just so sad because it's not the process that is quite so. I mean, it is challenging in itself. It's not just that. It's the fact that there's a lot of noise out there. There's a lot of other things that lead to electrons changing energy levels, for instance. And so, if you want to shield your whole experiment from light and neutrinos and all sorts of other cosmic rays that would have the same effect on your electrons, you're in trouble. That it's the reality of life in which we live in. If we were living in a much simpler universe where there was nothing other than electrons and gravitons, and there was no cosmic rays and even light, then it may have been easier to abstract yourself from any other noise and prove maybe the quantum nature of gravity.
Well, I think that would be a wonderful place to wrap up. There's so many interesting things we could explore in this wonderful new book. We'll have to do it perhaps in person someday. The Beauty of Falling is a beautiful book, A Life in Pursuit of Gravity, and it's endorsed by some of the past guests on the podcast, including Sarah Seeger and Sean Carroll. Both of them give it their most high encomium, as do I. Claudia de Rham, I hope you have a great deal of success with this wonderful book. And I think your students are lucky to have you, and your colleagues are lucky to have you. And it's wonderful to have an iconoclastic thinker that can operate as you do in the mainstream. You could talk to string theorists. You can talk to people that study loop quantum gravity or causal set theory, and you're not afraid to kind of push back respectfully, as I think is so refreshing. So this book is a wonderful addition. It's incredibly readable. I listened to it. Princeton University sent me the audio copy as well, which is not read by you, but is a delightful voice, whoever the narrator is. So I cannot recommend this highly enough.
Thank you, Brian. It was so much fun to talk to you. Thanks.
Hey there. I know if you watched all the way to the end, you're going to love this interview with Lawrence Krauss, one of the progenitors of the notion of dark energy. And click here for a playlist for the best episodes about cosmology and the origin of the universe. See you next time on Into the Impossible.